Hey there, welcome to another video, the last video in this entire series. Yes, feels good, right? Kind of done, moving on, a little, maybe you're sad, I don't know, a little bit sad. You can do more trigonometry like this. Don't worry, you will, because in calculus, ton of trigonometry. But this is important because we're going to talk about symmetry as it involves polar equations. You see, there's some equations, like that one, that when you translate them into rectangular, they don't work so well and they look really, really bad. Very hard to deal with. And you can try it. Go ahead and try to change that into rectangular equations. You'll see what I mean. You'll see how there's a couple hiccups and you go, what am I supposed to do with that? It's not a circle. It's definitely not a circle. And not an ellipse, not any of these conic sections we're used to. And so that's quite difficult. So what do? You leave it in polar and you learn symmetry. So here's the idea behind the following four examples. If these are too hard to change to rectangular, we're going to leave them, but we're going to learn about symmetry and then plug in some points to deal with a smaller section and use symmetry to kind of mirror it. So here's how symmetry works for polar equations. If your theta and negative theta, if you plug in negative theta and it gives you the same exact equation that you started with, so basically it acts like an even function. If that's the case, then you're going to have symmetry in your graph, and it's going to be symmetric about the polar axis or the x-axis. Now think about why that would happen. If you have a positive angle and a negative angle, and it gives you out the same exact points, you're going to be mirrored across this polar axis. It's going to give you the same exact values. That's like the x-axis. So we're going to check that first. If you plug in pi minus theta into your equation and it gives you the same exact thing as you started with, you're going to have symmetry about pi over 2. Now, hopefully that makes sense. Here's pi over 2, like this y-axis. Pi is 180 degrees. 0 is over here, your polar axis. If pi minus your angle is the same thing as your angle, then you're going to get symmetry across this mirror image across the y-axis. You'll have that. Very similar to what we did with the double solution for the side angle for sine, how that would give us these two solutions because we had 180 minus theta matching up with our theta with sine. That's exactly what this is talking about. Lastly, if you can change just the value of your r, the sign of your r, and it gives you the same exact answer as what you started, the same exact equation, then you're symmetric about the pole. Why? Because if your pole's here and r and negative r give you the same exact result, you're going to be symmetric about that pole. It's going to mirror image across that. 180 degrees would be identical. So this is the order of business for us, really. Check to see if you could change it into rectangular easily. Normally, when you have stuff added or subtracted, it's not easy and it won't give you anything very nice. So we can check that, but then go through all of our symmetry. So we're going to try it. We're going to try every one of these. I'll walk you through it very nicely. After you've checked symmetry, see what works, see what doesn't work, and it will limit the points that you have to plug in. So then I'll show you how to plug in certain values like negative pi over 2, negative pi over 3, negative pi over 4, negative pi over 6, 0, pi over 6, pi over 4, pi over 3, pi over 2. Get a series of points and then plug them in, plot them, and use your symmetry to mirror image. So we're going to start there. How about r equals 1 minus sine theta? Man, going to rectangular equations is possible, but it wouldn't give us anything nice because of that. If you multiply both sides by r, that would be easy. That'd be y. That would be easy. That'd be x squared plus y squared. That would not be easy. That would be r. You'd have a square root of x squared plus y squared. It's not nice to deal with, so we're going to avoid that. What we're not going to avoid is checking symmetry. So how we start with checking symmetry is really just with this, checking almost an evenness and oddness sort of idea. Take your theta and plug in negative theta. Just see what happens. So I'm going to replace my theta with negative theta. If this works out to be exactly the same equation that I started with, we will have symmetry about the x-axis or the polar axis. If not, then we probably won't. Now, get this. We probably won't. This is not a guarantee. If it doesn't work, it's not guaranteeing that you don't have symmetry, but you just can't use it because you're not sure. It's inconclusive. If it does work, we guarantee that we will have symmetry though, so that's nice. Now, I hope you remember about sine. Sine is an odd function. So sine of negative theta equals negative sine of theta. Which one's the even function? Cosine is. So if we had cosine of negative theta, it would give us positive cosine of positive theta. So for us, we go, okay, 1 minus sine of negative theta. Sine of negative theta is negative sine theta. It's going to change that sign. So we take a look at it. We've simplified it. Is this exactly the same equation that I started with? No. So this is probably not symmetric about the polar axis. Think x-axis. Probably not symmetric about the polar or x-axis. So then we move on. We deal with all three symmetries to make our lives as easy as humanly possible. So how about pi minus theta? You're going to have to use some identities here. We're going to see that right now. So I'm going to take r, I'm going to leave r alone. 1 minus sine. This says replace your theta with pi minus theta and see what happens. Remember, if we simplify this and get exactly what we started with, we will for sure have symmetry about pi over 2 axis or the y-axis. So let's deal with that. How in the world do you simplify that when you don't know your theta? This is where all those sum and difference formulas that I taught you come into play. So sine of pi minus theta, we would think, all right, let's see. Sine of pi minus theta, maybe have the formula sheet out, is sine of the first one, cosine of the second one, minus cosine of the first one, sine of the second one. But please remember that this is all in parentheses because this gives us this, so this is 1 minus all of that stuff. So sine of pi, oh my gosh. Sine of pi is the y-coordinate at pi. That's going to be 0. So this whole thing is gone. Pi of 0 is 0. Sine of pi is 0. 0 times cosine, I don't care, is 0. Minus cosine pi is negative 1. Sine of theta is sine of theta. So minus negative 1 sine theta. Now there's a lot of negatives going on, but this says opposite of negative 1 is positive 1. 1 minus positive 1 sine theta is 1 minus sine theta. That's exactly what we started with, which means that if this works, you are going to have symmetry about that vertical axis, the pi over 2 or the y-axis. Okay, last one to check. Take r and make it negative. If positive r equals negative r, when you change the sign of r, and you get exactly the same things you started with, you'll have symmetry about the origin or the pole. So let's do that. All that's required is we take this r and change its sign. Now let's solve for r. So divide everything by negative 1. Now this is clearly not what we started with. The signs are all opposite, which means we probably don't have symmetry about the pole. So after we've done that, we don't really have any better way to go about it than plotting some points. So why do we use symmetry in the first place? So you wouldn't have to plot all of the points. So you wouldn't have to plot pi over 6, 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, then pi, and then all of this quadrant, and then all of this quadrant. You see, here's what we learned. While we probably don't have symmetry about our x-axis or the polar axis, and we probably don't have symmetry about our pole, we do have symmetry about the y-axis or about the pi over 2 axis. So if we find all of these values, we can mirror them and we'll have all of these values. That's what the symmetry does. So we really only need to find values from negative pi over 2 to pi over 2. That's what we're going to do right now. If we find this half, we'll mirror it and find this half. That's what that says. You have symmetry about the y-axis, so just find one side. You could do this side for sure and mirror it here, but these are generally easier. So find the right side, flip it, and you'll get the left side. Because that's our only symmetry, that's the only way we can limit the points that we have to plug in right now. So we're going to take and plug in negative pi over 2, negative pi over 3, and all of these very common values and get those coordinates. So we're about to get going on it. Remember that polar coordinates are r comma theta. So we're going to plug in these angles, negative pi over 2, but they will be the second coordinate. How we plug them in is no different. We're going to take these values, we're going to plug them into our equation, we're going to see what happens. So I'll do a couple with you and then I'll write down some of the other ones that I'm getting, but here's the thought process. If this is an angle, and it's this angle right here, then if I plug in that angle, it will give me a distance from the pole. So let's do that. Plug in negative pi over 2. Sine of negative pi over 2 is negative 1. Negative 1. So 1 minus negative 1 is 2. What that means is that along this angle of negative pi over 2, you're going to get an r of 2. Can you plot that? Heck yeah. So at negative pi over 2, you're going to get an r of 2. That's going to give you this point. We plotted lots of these things. Negative pi over 2 is your angle, distance of 2 from the origin or the pole. You're going to have a point right there. That's our very first point. So we're going to plot all of those. How about negative pi over 3? Sine of negative pi over 3 is negative square root 3 over 2. 1 minus negative square root 3 over 2 is like 1 plus square root 3 over 2. Let's see. Square root 3 over 2 is like 0.87. So this is positive 1.87. I think it's 1.866 something, but one thing right now, please don't confuse positive values with negative y values. This is r theta. So what this says is go to an angle of negative pi over 3, got it. Then along that ray, you're going out positive 1.87. So if this is 2, 1.87 would be a little shorter, probably right about here. Let's do negative pi over 4. Sine of negative pi over 4 is, let's see, negative square root 2 over 2. 1 minus negative square root 2 over 2 is 1 plus square root 2 over 2. That's about 2.41. No, it's not. 0.7. Let's see, square root of 2 is 1.41. Half of that is 0.405-ish, 0.705-ish. So let's say positive 1.7. Somehow I forgot negative pi over 6. So that's slightly closer to that pole. Let's plug in negative pi over 6. Sine of negative pi over 6 is negative 1/2. So 1 minus negative 1/2, that's 1 plus 1/2. That's 3/2, or 1.5. That's a little bit closer to that pole. How about 0? Remember, we're plugging in angles here. That would be an angle of 0. That's on the polar axis. So let's take 0, let's plug it in. Sine of 0 is 0. 1 minus 0 is 1. So at an angle of 0, the distance from your pole is 1. That's what r theta is telling you. Now for positive angles. With pi over 6, sine of pi over 6 is 1/2. 1 minus 1/2 is 1/2. Hopefully it's clear now, we do not have symmetry across this polar axis. And that's because we're subtracting sine, and sine is not symmetric about that. The signs of the y values are opposite, so we don't have that symmetry. Let's try pi over 4. Sine of pi over 4, if we're going to plug that in, sine of pi over 4 is square root 2 over 2. That's 0.707. 1 minus that is like close to 0.3, but like 0.29. It's getting pretty close to that pole. How about pi over 3? Sine of pi over 3 is square root 3 over 2. That's 0.87-ish. So 1 minus 0.87 is about 0.13. That's really close. And then finally, we're almost done. Pi over 2. Sine of pi over 2, remember, this is what we're doing. We're plugging our angles into there to get our r. That's our distance from the pole. Sine of pi over 2 is 1. 1 minus 1 is 0. So that says, at an angle of pi over 2, you are at that pole. So if we graph this, don't graph it with straight lines, graph a nice smooth curve. It's actually a really pretty graph. So we have plotted all of those points by taking some really common values, negative pi over 2, negative pi over 3, all of these values from negative pi over 2 to pi over 2, getting our r's from there, and these all say at a certain angle, this is how far away you are from the pole. So we've shown that. Now we're going to plot a smooth curve. But that's only half of it. You see, because we know about this symmetry, we get to avoid plugging in all of these values, which actually would take quite a long time. I did in my head, I know, but like this would take a little while. So because we know symmetry, just draw a mirror image. You can draw all of these other values and actually put the points down. Most of the time, I wouldn't do that. I would just kind of sketch it and make sure it's symmetrical. That's about as good as I can do. What that's called is called a cardioid. So r equals 1 minus sine theta gives you something called a cardioid. Why? Because it kind of looks like a heart. I hope it makes sense. I hope that you're understanding the idea of that's real hard to look at as a rectangular equation. It's not good. So we're going to leave it in polar, but that requires a few things from us. It requires us to check symmetry, to use symmetry if it does work, and plug in some values that take advantage of that. Symmetry allows you to save work, not make more work, because otherwise you'd have to plug in all of these values around a unit circle. It's very challenging. We don't want to do that. So identify symmetry, limit what you have to plug in known values on a unit circle, make it easy on yourself to do the math, and then mirror image those across the symmetry that you've identified. Okay, let's try another one. So we've got r equals 1 plus 2 cosine theta. We're looking at this thinking rectangular equation, nah, not so much. It's going to be really hard to do. Without that, absolutely, it'd be pretty easy to do. We have r squared equals 2r cosine theta. If we multiply both sides by r, it'd give us some sort of a circle. Not too bad. That, not so much. So we're going to check symmetry, plug in some points, and then graph it with our symmetry. The first one we always check is almost an evenness idea. Plug in negative theta and see what happens. Now, cosine's an even function, so cosine of negative theta gives you cosine of positive theta. So cosine negative theta, cosine positive theta are the same thing. That means I can change my argument without changing my function. So because cosine's even, opposite inputs give you equal outputs. This is still the same thing as 1 plus 2 cosine of positive theta due to the evenness of cosine. Now, that's exactly what we got here. What that says is that this function will be symmetric about the polar axis or about the x-axis. We're going to try other symmetry. We're going to try symmetry about the y-axis or the pi over 2 axis. So we're going to plug this pi minus theta in, use a sum or difference formula, and then simplify. So 1 plus 2 cosine pi minus theta. We need the sum or difference formula for cosine. The difference formula for cosine says cosine of the first, cosine of the second, plus sine of the first, sine of the second. But remember, this 2 would be multiplied by all of this. So let's take a look. Cosine of pi, that's -1. So this would be negative cosine theta. Sine of pi is 0. So this whole thing disappears. We get r equals 1 plus 2. Remember, this is -1, negative cosine theta. If we simplify just a bit, r equals 1 minus 2 cosine theta. While that's close, that is not exactly what we have here. So this is probably not symmetric about that pi over 2 or the y-axis. How about the negative r? You know, sometimes we can just look at it and think, if that's negative, these signs would both change. That's not going to help me at all. That's not going to be symmetric. So this is not going to be symmetric about the pole or the origin. So dividing both sides by -1, that's not going to work. So this is probably not symmetric about the pole. After that, we're just going to plug in some values, but notice what happened. Because we know we're symmetric about this polar or the x-axis, think x-axis, we really only need to know these important values from 0 to pi, and then we'll be able to mirror them. So we're going to plug in 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. You can get away with doing just some of these if you're careful. So sometimes I just omit doing pi over 4 and 3 pi over 4 because these values do enough for me. So you can do that, but to get the best picture possible, plug in all the ones on the unit circle. Okay, so let's get started. Remember what we're doing. We're plugging in angles, figuring out r from our function. That's what it tells us. It says r in terms of theta. It says you can plug in theta and figure out an r. What that gives you is an ordered pair. R comma theta says go along that angle that far, whatever we figure out. So let's plug in 0. Cosine of 0 is 1. 2 times 1 is 2. 2 plus 1 is 3. This says go to an angle of 0 and then go from the pole 3 units along the angle. Okay, now we're going to plug in pi over 6. Cosine of pi over 6 is square root 3 over 2. 2 times square root 3 over 2 is just square root 3. Square root 3 is about 1.73. So 1 plus 1.73 is about 2.7. Or 2.73. So this says, along that angle, go to the angle of pi over 6 and go out 2.7 units, or thereabout. Pi over 4. Cosine of pi over 4, right here, is going to be square root 2 over 2. Square root 2 over 2 times 2 is just square root 2. That's 1.4. 1.41. 1 plus 1.41 is like 2.41. So this says along that angle, pi over 4, you're going to go out 2.4. Pi over 3, cosine of pi over 3 is 1/2. 2 times 1/2 is 1, and 1 plus 1 gives you 2. So along this angle of pi over 3, we're going to go out from the pole, from the origin, 2 units. Now we're going to jump to pi over 2. So when we plug in pi over 2, cosine of pi over 2, that's 0. 2 times 0 is 0, but 1 plus 0 is 1. So along this angle of pi over 2, it says go to pi over 2, you're going to go up 1 unit along that ray from the pole. Now, 2 pi over 3. So when we plug in 2 pi over 3, cosine of 2 pi over 3 is -1/2. 2 times -1/2 is -1. 1 minus 1 is 0. So if I plug in 2 pi over 3, I'm going to get 0. And here's where things get interesting. So At 2 pi over 3, I get 0. So along this ray, 2 pi over 3, I'm going to get right at the origin. Okay, let's try 3 pi over 4. Cosine of 3 pi over 4 is negative square root 2 over 2. Times 2, that's going to give you negative square root of 2. It's negative 1.41. 1 plus negative 1.41 is negative 0.41. We go, how in the world do we graph negative 0.41? Remember, these are polar coordinates. It says go to your angle, 3 pi over 4. Negative r would say, go along this ray in the opposite direction of 0.4. How about 5 pi over 6? Same thing's going to happen here. Cosine of 5 pi over 6 is negative square root 3 over 2. 2 times that is negative square root 3. That's negative 1.7. 1 plus negative 1.7 is negative 0.7. So we get negative 0.7. What that means is that we would go to 5 pi over 6. That's this ray right here. Negative r, though, says don't go along that ray. Go along the opposite one from it. Negative 0.7 in this case is along this part, 0.7 units. So we've done that. Last one, let's plug in pi. Cosine of pi is negative 1. 2 times negative 1 is negative 2. 1 minus 2 is negative 1. So what this says, polar coordinates, go to pi all the way to here. Instead of going along the ray 1, go in the opposite direction. That puts you right there. Now this is kind of weird because we sort of cross over this axis of symmetry. So be smart about it. We're going to plot the curve first. We're going to graph the curve first that we've got. So it's a nice smooth curve. But then we're going to use our symmetry. Our symmetry says, remember, we're symmetric about this axis, but in both cases, the stuff above goes below, the stuff below goes above. So we're just going to mirror image this thing. I've done my best to mirror image that. Of course, you could plug in the values, but it can get a little confusing. What this is called is lemison with an inner loop. So that's the inner loop that we have right there. I'm hoping it makes sense. We're going to try one more symmetry to make sure that you get it, and then an example to wrap everything up. Let's keep right on going. So we've got r equals 2 cosine 2 theta. We might think about rectangular equations, but that makes it pretty difficult because that would change into one of our double angle formulas and get a little bit hairy. So we don't really want to do that. Instead, let's take a look at our symmetry. And we're going to find some very interesting things about this. We'll start with plugging in negative theta and see what happens here. So r would equal 2 cosine of negative 2 theta. So negative theta would create negative 2 theta. Cosine's still even though. So opposite inputs give you equal outputs. That means we can change the sign of our argument without changing the sign of our function. So cosine negative 2 theta is exactly the same thing as cosine of positive 2 theta. And that means we're going to have symmetry about this polar axis, or the x-axis if you can want to think about it that way. Now we're going to try plugging in pi minus theta, use a difference, sum or difference formula, and figure out what happens. And we end up getting 2 cosine 2 pi minus 2 theta. Now, before we get all crazy about, man, I got to use some sort of formula here, generally you do. Like, if we didn't have that too, you probably would. But I want you to notice something. This is the same thing as negative 2 theta plus 2 pi. What's the period of cosine, though? The period is 2 pi. Do you remember that you can add or subtract 2 pi from cosine or sine and get exactly the same value? What that means is that 2 pi, if I subtract that out of here, it's going to give me exactly the same thing as cosine of negative 2 theta. So let's subtract the 2 pi. So whether you have 2 pi in there or subtract it out, it's going to give you the same value, such as, let's see, cosine of 0 or cosine of 0 plus 2 pi or cosine of 0 plus 4 pi is going to be the same exact thing. We can subtract 2 pi and be just fine. Now, how about cosine of negative 2 theta? Again, it's an even function. So opposite inputs give you equal outputs. This is the same as 2 cosine 2 theta. But that's exactly what we started with, which means not only do we have symmetry across the polar axis, we also have symmetry across the pi over 2 axis, or the y-axis. Now, I'm going to say something that's got to make sense. If you have symmetry across the x-axis and you have symmetry across the y-axis, you will definitely have symmetry about the origin. And the same thing happens here. If you have symmetry about the polar axis and you have symmetry about the pi over 2 axis, you are going to have symmetry about the pole, and you don't have to check it. Yes. So what are we going to find? Well, this is great. If we have symmetry this way, we only have to check this side of our unit circle. But if we have symmetry this way, we only have to check this side of our unit circle. So really, we just have to check the first quadrant. That's it. What are these here for? Well, because we're going to get some negative r's, and this is a little bit nice to use. If you have negative r's, you have these already. So we're going to check just the first quadrant. So we're going to plug in some angles. We're going to figure out the r, or the distance from the pole along those angles, and we'll be able to plot this and then use all of our symmetry. So let's plug in 0. 2 times 0 is 0. Cosine of 0 is 1. 2 times 1 is 2. So what this says is that along the angle of 0, you're going to go 2 units. Plug in pi over 6. 2 times pi over 6 is actually pi over 3. Whoa, that's going to be a little different when we get to some of these. It's going to act like bigger angles. That's where our negatives are going to come from. So 2 times pi over 6 is pi over 3. Cosine of pi over 3 is 1/2. 2 times 1/2 is 1. So along pi over 6, we would go out 1 unit. Let's go to pi over 4. 2 times pi over 4, well, let's see, that would be pi over 2. Cosine of pi over 2, that's 0. 2 times 0 is 0. This says go along pi over 4, but you're not going along it. You're going 0 from it. So you are at the pole. Let's check out pi over 3. 2 times pi over 3 is 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. 2 times negative 1/2 is negative 1. So this says go to your angle. Go to pi over 3. Got it. Instead of going positive 1 in the direction of your angle, go in the opposite direction of your angle. So 1 unit in the opposite direction of your angle. And now pi over 2. So 2 times pi over 2 is just pi. Cosine of pi is negative 1, and 2 times negative 1 is negative 2. So this says go to pi over 2. Instead of going along the positive ray, go along the opposite. Go down here to negative 2. So we're going to graph this. But then we're going to use symmetry. Use all the symmetry that you have. This is symmetric about the x-axis. So what would that mean? This would reflect here. This would reflect here. But you're also symmetric about the y-axis. This reflects here. This reflects here. And this reflects here. You get what's called a rose. So this is what we call a rose in in polar equations. So it's kind of nice using that symmetry. You just make it all symmetrical with itself across the y-axis and the x-axis, or the pi/2 axis and the polar axis and the pole, and we would get a pretty nice shape out of that. It's not perfect, but I did my best. Hopefully you're enjoying it and you're seeing the usefulness. Before we get to the last example, I'd like for you to do it on your own. The idea is check your symmetry first. It limits what you actually have to plug in. Then plug in the least amount of points you possibly can. Usually it's 2 quadrants. We got lucky here, we got 1 quadrant. And then use your symmetry to mirror that graph. So we'll come back with one more example. All right, last one. I gotta show you one that's symmetric around the pole. I ruined it, but you're gonna see why it is in just a second. Let's go ahead and do this. We're gonna just not even worry about our rectangular equations from this, because it'd be pretty crazy, especially with that 2 theta going on. So let's check symmetry. First thing we always check, plug in negative theta, evaluate that, see if it's the same. So if we're gonna evaluate, then r squared equals 4 sine of negative 2 theta. And most of the time, when you get used to this, you can do them in your head just by the nature of what sine and cosine do. So if you think, I'm going to change the sign in an odd function, it's going to change the sign of my function. So this would be negative 4 sine 2 theta, because sine's odd. Opposite inputs give you opposite outputs. Change the sign of your argument, change the sign of your function. And what that means is this is probably not symmetric about the polar axis. Let's try the next one. Let's try pi minus theta. We're going to evaluate that. And we get something very similar to the last example, that we have 2 pi minus 2 theta. Sine's period is 2 pi. It means you can add 2 pi or subtract and just remove that entire thing and get the same result. So we can subtract 2 pi from this, from the argument, and get the same exact output for sine, which means we can eliminate that piece. But if we do, it actually brings us back to right here, which we already know the result. And that's clearly not what we started with. So this is probably not symmetric about the pi/2 axis either. Now, what about negative r? I already ruined it, but if you evaluate negative r, then negative r would be squared. Now, it doesn't affect the right-hand side at all, but negative r squared is the same thing as r squared. This is symmetric about the pole. Since we have symmetry about the pole, we need to check 2 quadrants, 2 consecutive quadrants. It doesn't really matter which ones you choose, but if we check these 2 quadrants, we can use symmetry to find these 2 quadrants. If we check these 2 quadrants, we use symmetry to find these 2 quadrants. So you just need to check 2 of them. I'm going to choose to check from 0 to pi because those are easiest for me to plug in. So let's go ahead and start doing it. Remember, these are polar coordinates. You're plugging in angles and finding out distances from the pole, and then we can plot those. So an angle of 0, if we evaluate that, 2 times 0 is 0. Sine of 0 is 0. 4 times 0 is 0. The square root, that's a big deal. The square root of 0 is 0. So this says, at an angle of 0, you are at the pole. Now let's plug in pi/6. If we evaluate pi/6, 2 times pi/6 is pi/3. Sine of pi/3 is square root 3 over 2, and 4 times that is 2 times square root 3, so 2 square root 3. Let's see, that's 1.7 times 2. about 2.8. But notice something. This would be r squared equals 2.8. How would you find r? You take a square root. But in doing so, when you take a square root, you have to do a plus and minus. That is precisely why this is symmetric about the pole. I need you to see it. If you go to pi over 6, you're going to get plus or minus the square root of 2.8. I worked out on the calculator. I got about plus or minus 1.9. So here's what this says. Man, get it. Get the relationship with symmetry about the pole. This says go to your angle pi over 6. Here's pi over 6. You're going to go out about 1.9. There's about 1.9 and negative 1.9. So here's pi over 6 positive 1.9 and negative 1.9. That right there is what is going to give you symmetry about that pole, is because you have plus and minus, because you go both positively and negatively. Could you have just found the positive and counted on symmetry to find the negative? Yes, you totally could have done that as well. Let's try pi over 4. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. Let's see, 1 times 4 is 4. R squared would equal 4. R equals plus or minus 2. The square root of 4 plus or minus 2. So here, at pi over 4, this says you're going to go out 2 along the ray and out 2 in the opposite direction of that ray. So here's pi over 2, go out 2 units. And negative 2 units. That's causing the symmetry about the pole. Let's do pi over 3. So 2 times pi over 3 is 2 pi over 3. Sine of 2 pi over 3. Let's see. Sine of 2 pi over 3 is square root 3 over 2. 4 times square root 3 over 2 is 2 square root 3. So r squared equals 2 square root 3. R therefore would be plus or minus the square root of that. That's exactly what we got here, by the way. So plus or minus 2, the square root of 2 square root 3 is what we get. That's again about plus or minus 1.9. So we're going to do the same thing. Along pi over 3, here we go, along pi over 3, go out 1.9. And in the opposite direction of pi over 3, go out 1.9. So negative 1.9 puts you on that ray in the opposite direction. Now, how about pi over 2? If we evaluate pi over 2, 2 times pi over 2 is pi. Sine of pi is 0. So 4 times 0 is 0. R squared is 0. Square root of 0 is still 0. So we're going to get 0. Now, we already have 0. That's okay. Let's try the next one. You're going to see something interesting happen. Try 2 pi over 3. When we evaluate 2 pi over 3, even though 2 pi over 3 is right here, 2 times 2 pi over 3 is 4 pi over 3. Now, sine of 4 pi over 3, 1, 2, 3, 4, is negative. Please get this. Sine of 4 pi over 3 is negative square root 3 over 2. 4 times negative square root 3 over 2 is going to give you negative 2 square root 3. But look what you have. If you have r squared equals negative 2 square root 3. So again, that's, let's see, 4 pi over 3, sine of 4 pi over 3 is negative square root 3 over 2. 4 times that is negative 2 square root 3. If r squared equals negative 2 square root 3, take a square root. What's going to happen? You take a square root of this thing, you're going to have a negative inside of a square root. That's an imaginary number. This can't happen here. That's going to be imaginary here. These are all imaginary because sine of those values, 2 times, 2 times 3 pi over 4, that's going to give you 3 pi over 2. Sine of 3 pi over 2 is negative. Square root, an r squared equal to a negative. Square root of a negative is imaginary. Same thing, 5 pi over 6. Multiply by 2, that'd be 5 pi over 3. Sine of 5 over 3 is negative. R squared equals to a negative. Square root would give you imaginary number. Same thing with pi. 2 times pi would be 2 pi. Sine of 2 pi would give you 0. So, I mean, that gives you 0, but you already have 0. So, no matter what you do with these, you're going to get imaginary numbers. These are non-points for you, which is why this graph is only going to exist in 2 quadrants, 1 and 3. 1, because the values of sine are positive and square roots are positive, makes sense. 3, because we know it's symmetric about the pole, and we get those negative r for those angles. 2 and 4 do not exist. Why? Because sine right there was negative for those values, and when you reflected them, it doesn't make sense to reflect an imaginary number. It doesn't make sense to plot an imaginary number on our polar coordinates. So we just really have this graph. It's called a lemniscate. So kind of interesting. I hope that it makes sense. I hope especially you understand that when you plug these in and it gives you a negative and r squared equals a negative, the square root of a negative number is imaginary, and we cannot plot that on our polar coordinate system the way we have it designed. So I hope that this has made sense. I really hope that you understand about the symmetry. It's kind of fun. I think it's fun, useful, and it will allow you to graph some of these polar equations without translating to rectangular and having a very hard time doing it. So find your symmetry, limit the amount of points you plug in, then use your symmetry. Hope it makes sense. I hope you've enjoyed this video. I hope you've enjoyed this series. Have a great day.